Hi, welcome to my introduction to software algorithms. So what's an algorithm? Well, put simply, an algorithm is a sequence of steps required to solve a problem. So consider your routine for getting ready in the morning. Step 1 might be getting out of bed. Step 2, brushing your teeth. Step 3, having a shower. 4, getting dressed. 5, having your breakfast. And then 6, leaving the house. So that might be your algorithm for getting ready in the morning, or something similar. In this video, I'm going to present some well-known software algorithms on this board. And for each, we're going to analyse its time complexity. In other words, how long does the algorithm take to execute relative to the size of its input? Now, we're not going to get into any formal definitions in this video. That will come later. For now, I just want you to develop a basic understanding. So stay tuned. Okay, a nice simple one to start with. Here we have a function named isFirstElementEven, which takes an array of numbers and the length of the array as arguments. Now, all this function does is it returns whether the first element in the array is even or not. So what would be the time complexity of this algorithm? Well, retrieving array elements by their index is a constant time operation, as the amount of time required to do so is not relative to the size of the input. Now, for the purpose of this discussion, we'll assume that constant time operations take a single unit of time to execute. So this algorithm is a constant time algorithm. So here we have a function named findElement, which takes an array of numbers, a target to search for in the array, and the length of the array as arguments. Now, this function contains a loop, which iterates through the array from start to end. Now, for each element, we ask whether that element is the target we're looking for. If it is, then we exit the loop and the function indicating that our search was successful. If the array doesn't contain our value, then we exit the function indicating that our search was unsuccessful. Now, let's use the example here to trace through our algorithm. Here we have our list of numbers. We have the target we're going to search for, which is number 7, and the length of the array, which is 4. Now, to begin, we start at the first element, and we ask whether that element is the target we're looking for. Well, it isn't. So we move on to the next element, and we ask again, is that the target we're searching for? No, it isn't. So on to the next one. Not our target. On to the next one. It's not our target. And then we're out of bounds. So what would be the time complexity of this algorithm? Well, in the worst case, we traverse the entire array. For example, if there was one element, we'd execute this check once. If there were 10 elements, we'd execute it 10 times. 100 elements, 100 checks, and so on. Therefore, here you can see that the time required is directly proportional to the length of the array. Therefore, this algorithm is a linear time algorithm. Okay, so here we have a method named printPairs, which takes an array of numbers and the length of the array as arguments. Now, this method contains a nested loop. So you'll see the outer loop and then the inner loop within. Then within that, we have a print statement which simply prints out the numbers as both loops traverse the array. So let's use the example here to trace through our algorithm. Here we have our array of numbers and the length of the array, 2. Then here we have a table with I and j columns representing the outer and inner loops respectively, and an output column so we can record what's being printed. So, to begin with, both loops will start at the beginning of the array. We can then print out the values at those indices. Now, we increment j, however I stays where it is, as we only increment I once j is past the end of the array. And we can print out the values again. Now, j's reached the end of the array, therefore we can increment I, and then j will start at the beginning of the array again. And we can print out the values. Now we can increment j. And we can print out the values. So what would be the time complexity of this algorithm? Well, for an array of length 2, we had 4 print statements. For an array of length 3, we'd have 9 print statements. And for an array of length 4, we'd have 16 print statements, and so on. Therefore, the time complexity of this algorithm is quadratic. Final example, and in this one we'll turn things up just a notch. Here we have a function named searchSorted, which takes a sorted array, a target, and the length of the array as arguments. So what does the code do? Well, to begin with, we declare 2 variables, start and end, which point to the beginning and the end of our search space respectively. We then encounter a loop. Now, the code here within the loop will execute while start is less than or equals to the end. We'll then declare a middle variable, which will point to the middle of our search space. We'll ask whether the middle element is the target we're searching for. If it is, then we'll exit the loop and the function, indicating that we'd found our value. If the middle element is larger than our target, then we'll truncate the right-hand side of our search space. Otherwise, we'll truncate the left-hand side of our search space. If our array didn't contain our target, then we'd exit the function, indicating that our search was unsuccessful. So let's use the example here to trace through our algorithm. Here we have our array of numbers, all sorted in ascending order, with the target we're going to search for, 1, and the length of our array, 8. So first of all, let's point start, middle and end to the correct locations. We'll then ask whether the middle element is the target we're searching for. Well, it's larger, so we'll truncate the right-hand side of our search space. We'll then iterate around again, and we'll point middle to our middle element. We'll then ask whether the middle is our target. Well, it isn't, so again, we'll truncate the right-hand side of our search space. We'll then iterate around again, and we'll point middle to the middle of our search space. Again, middle is larger than our target, so we'll truncate the right-hand side of our search space. Now, start exceeds the end, therefore we'll terminate our loop. We'll also exit our function, indicating that our search was unsuccessful. So what would be the time complexity of this algorithm? Well, let's use the table here to help analyse exactly what's happened. Now, here we have two columns with iteration representing our iteration number and size representing the size of our search space after each iteration. Now, you'll recall after the first iteration, we reduced our search space down by roughly half to 4. After the second iteration, we reduced our search space down by roughly half again. Then after the third iteration, we reduced our search space down by roughly half again. Now, you notice a relationship between the iteration number and exponent in our denominator. For example, after the first iteration, we reduced our search space down to n divided by 2 to the first power. Then after the second iteration, we reduced our search space down to n divided by 2 to the second power. Then on the third iteration, we reduced our search space down to n divided by 2 to the third power. And then we stopped. When did we stop? We stopped when we had one element remaining, i.e. when n divided by 2 to the third power equals 1. Or in other words, we stopped when n divided by 2 to our iteration number equals 1. So let's write that down. Now, I've used the letter K to represent the iteration number. It's a common convention. Now, K, or our iteration number, represents the amount of work that was done, i.e. our time complexity. Therefore, to solve this puzzle, we need to solve for K. Now, first of all, we'll multiply both sides by 2 to the K. Here, the 2 to the K's will cancel, and 1 will cancel also. Therefore, we're left with n equals 2 to the K. Now, here, K is an exponent. Therefore, to solve for K, we need to take the logarithm of both sides. So let's do that. Now, using exponent rules, or logarithm rules, we can rewrite this portion here as follows. Right. K times log base 2 of 2. Now, log base 2 of 2 is 1. Therefore, we can reduce this portion here to K times 1. Therefore, what we're left with is K equals log base 2 n. So there we have it. The time complexity of this algorithm is log base 2 of n, a logarithmic algorithm. So let's use this graph to compare the algorithms discussed in this video. On the x-axis, we have our n, which was the input size. On the y-axis, we have our time complexity. Now, if you recall our first example, the algorithm which detected whether the first element in the array was even or not, well, that was the constant time algorithm, which represented here as a flat line, as the output was the same for every input. Then the second example, which was our search across the unsorted list, well, that was the linear time algorithm, which is represented here as a diagonal line, where there's a constant rate of change between the input and the output. Then the third example, our printPairs algorithm, well, that was the quadratic time complexity, which if we look close is the right-hand side of a positive parabola. And then finally, with our logarithmic algorithm, the algorithm which performed our search across the sorted array, which represented here. Now you'll see in this curve, the rate of change starts at high, but then gets less and less as n grows large. Now, in the next video, we're going to step things up even further by discussing how we can analyze the time complexity of recursive algorithms. So if you like this video, like and subscribe. If you have any queries or suggestions, leave a comment. And until next time, bye-bye.